Okay, so I'm going to tell you about something that I work on in my research lab downhill at the Advanced Research Complex, which is called super-continuum generation. So basically what that is, that's where you get a very highly broadened spectrum of light by putting it through a specialized dispersive optical fiber in which there are nonlinear effects that include, but are not limited to, self-phase modulation, stimulated Raman scattering, and parametric four-wave mixing. And of course those all interact, so that's really all you need to know, right? But unfortunately, even those things, they have very complicated mathematical equations to describe them, and they all couple in ways that are kind of hard to conceptualize. So I'm going to try and break it down into a few simple analogies. So what I want you to imagine is you have paint, but all you have is red paint. And you'd really like to make some kind of nice picture, and you want to be able to have rainbow colors, right? But you only have red paint, and you don't have anything to mix it with. So it's looking like you're gonna have something monochromatic. But what I need you to remember is that light and color are very closely tied together. What we perceive as color is basically the frequency of the light that comes back to our eyes that we can detect. So when I say color, what I'm really referring to is frequency. And then when I say we have red paint and that's all we have, what I really mean is the lab that I work in has a laser. And lasers typically have not a very broad spectrum. It's kind of just one color, and ours happens to be in the near infrared. And so when I say how do we have more colors to paint with, what I mean is how do we broaden that spectrum so we'll have all those colors available to us. So how do we get new frequencies of light? So I have a little example. So this is with acoustic waves, not light waves. So they're kind of different, but the concept is similar. I'm going to play you one frequency. Okay, so we hear that. Now I'm going to play you another one. It'll sound really similar. Similar? Can you hear they're slightly different? Maybe? Okay, but what happens when I play them both at the same time, added together? Okay, so you hear this modulation. It's kind of coming in and out, and you hear that. That corresponds to the difference in frequency between the two original things I played you. So that's what I mean when I say, okay, we're putting something in, we're putting our laser frequencies in, and we're getting something different out. So that's what I mean when I'm thinking frequency mixing. Of course, acoustic waves and light waves are very, very different and have very different properties, but that's just kind of to get you thinking, okay, we can mix things. So next, we remember that light, it's an electric field, it's a wave, it oscillates, propagates, makes a wave. And then the other thing is that in physics, pretty much everything can be a spring if you try hard enough. That's a very important concept. Okay, so in this case, the spring, that's the electron and the nucleus. So we know that the electron is kind of bound to the nucleus. It kind of, floats around outside, but it doesn't want to get too far away. Hence, spring. So we know that we can kind of compress it, right? And when it gets too close to the nucleus, there's strong repulsion because proton, positive charge, electron, negative charge, so then they're going to want to spring apart again. And also, if we pull them too far away, obviously I brought a spring that's really too stiff and my arms are not strong enough to demonstrate, but if you pulled it too hard, the spring would break, so that's sort of, you can think of that as being the electron has been completely torn out of the atom. And what happens when we have an electric field that's oscillating and it comes through a material that has electrons? So you're going to have something like this, right? It kind of sways in and out. So the light can kind of transfer energy to the electrons in the medium, and they kind of sway up and down like this, right? That's fine. And then, okay, so that's fine in a linear type of response. But when I said nonlinear interactions, well, the laser beam, it comes out in really short pulses. So that's a lot of energy in a very short period of time, and also we focus it into an optical fiber, and that's like a strand of glass that's about twice as thick as a human hair. So it's tiny. That's a huge amount of energy, a lot of power focused into a tiny, tiny spot. So those electrons, they're not just swaying up and down, they're bouncing around in funny patterns. And so what actually happens is instead of having the same frequency in and out, you start to get new frequencies. And I just wanted to show you, so that's all I really have to say. We can input one laser frequency in the near infrared that we can't even see. And as it propagates through the fiber, well, you get some interesting things happening. I brought in a terrible resolution picture for you. But this is where we go into the fiber. And as it propagates, you have it going into the red, because that's the closest to the near infrared. But we start getting more and more frequencies, so we're following it around into the yellow and the green. And so at the end, it's got all of these colors all mixed together, but we just happen to, because of the way the camera is positioned, we see those more than others. And it's even cooler than that. We're not just going from the infrared into the visible part of the spectrum, because you need conservation of energy. So the visible part of the spectrum is actually more energetic than farther away. So if you're spreading one way, you have to spread the other way to compensate. So that's how we end up with this super broadband, multicolored laser after this specialized optical fiber. Okay, thank you.
Ooh.